So it turns out that thermodynamics and equilibrium are connected. They're really saying the same thing. And so our next goal is to talk about how free energy and equilibrium are related. This is described in your book in section 16.4, and I've divided our discussion into kind of two chunks to make it a little bit easier to digest. So this is the first one, and we're going to talk about calculating delta G from delta G equals negative RT ln K, and using that to predict the direction of spontaneous change, how both delta G and K are helping us to determine that. So once again, we're working through all of these possibilities for calculating delta G. A long time ago, in what seems like a galaxy far, far away, we talked about how whether you started with all reactants or started with all products, either way, your reaction was going to proceed toward equilibrium. And so this is a figure from your book in chapter 13. And so you see on the left side, we start with SO2 and O2, which were the reactants in this case. And on the right side, we start with just SO3, which was the product in this case. And you see in both cases, they end up at the same place. And we called that place equilibrium. So here's a different graph. On the y-axis, we have the free energy of the reactants and the products, so free energy. And then on the x-axis, we have pure reactants and pure products. So you might call that reaction progress. And you see that if you start with pure reactants, you'll go spontaneously toward the minimum delta G. And if you start with all products, you'll proceed in the reverse direction, toward the minimum delta G. So in both cases, in all cases, a system achieves the lowest free energy at equilibrium. So equilibrium means the lowest free energy. Beginning with pure reactants, the reaction moves toward the products. Beginning with pure products under standard conditions, the reaction moves toward the reactants. So the reaction can be spontaneous in either direction as long as it is moving toward equilibrium. Another way of saying that is that delta G and K are both saying the same thing. We can express their mathematical relationship here that delta G equals negative RT ln K. So again, the equilibrium occurs at the lowest value of free energy available to the reaction system. Okay, so let's think about this conceptually. Let's say you remember that delta G is related to RT ln K, but I stop you on the street, assuming we can be together on the same street, and ask you, I can't remember, is it RT ln K or negative RT ln K? Can you figure out the correct sign? Okay, so we said that for a reaction to be spontaneous in the forward direction, that means that delta G is negative. Okay, and we also said that something that is more favorable on the product side, that goes closer to completion, that completion, more to the products, is a large K. Or put another way, 10 to the large power. Okay, so if the exponent is bigger, then that means that the reaction is more favorable in the forward direction. We might say it's more spontaneous in the forward direction. Okay, so give this ln K part is helping us focus on the exponent. And then R and T are just numbers. Okay, so if delta G, if a larger exponent means more favorable, then that means a negative delta G. But the exponent is going to be a larger positive number. So that must mean that we need the negative sign because more negative delta G means a more positive exponent on K. So more negative delta G equals more positive, larger larger exponent on K. Okay, so that means that we need that negative sign because those are moving in the opposite direction. So we see that we could, for any value of delta G, we could calculate K. And so that as delta G gets more negative, then the exponent on K gets bigger. As delta G gets more positive, the exponent on K gets smaller. And so then if the standard delta G is a small negative value, then that means that the reaction proceeds a little bit toward the products to get to equilibrium. If it is a really large positive value, then the reaction basically stays at the reactants. It doesn't proceed at all. Okay, so here's a biochemical example. When gastrointestinal x-rays are taken, the patient often ingests a barium sulfate slurry. We say slurry because barium sulfate is not soluble, so it's kind of like a barium sulfate milkshake. The barium sulfate is opaque to x-rays, and that allows the radiologist to see the digestive tract clearly defined, so that way you could be looking for something like a blockage. Now, turns out that barium ions are toxic as ions, because they're kind of similar to calcium. They can interfere. But barium sulfate is basically insoluble, so this is okay. So, if you know the delta G of this reaction where barium sulfate solid becomes barium 2 plus and sulfate 2 minus, then can you calculate the value of KSP to see if it's insoluble? Okay, so it turns out that you can. This reaction, the K happens to be KSP, but the point is it can be any K. So here we can start with delta G equals negative RT ln K. And so here you'll see that we have a delta G prime, and that little prime indicates that we're really interested in 37 degrees C. I mentioned before that standard conditions usually means 25 degrees C, but in biochemical examples it means 37, and so that's what the little apostrophe is there for, a little caret or tick mark. Okay, so we want to solve for K. So let's rearrange this equation. We'll divide both sides by negative RT. So we get ln K by itself, and we have negative delta G standard prime divided by RT. And then to get rid of the ln, remember we need e. So we'll raise both sides to the e power, those will cancel, and we'll get K equals e to the negative delta G over RT. So now let's fill that in. Negative delta G, so delta G here is 59.1. We're going to make that joules, so convert to joules per mole, divided by R. Which value of R do we need? The one that has joules. 8.314 joules per mole times Kelvin. And we need the temperature in Kelvin, so we'll make that 310. All right, if we calculate that, we'll find that K equals 1.1 times 10 to the minus 10. So that K value tells us that this reaction basically stays at the reactants. Barium sulfate is pretty insoluble, which is good for you because barium is toxic. And also, we get the same value, roughly, that you would find if you looked this up in your KSP table at the end of your book. Okay, so here, you see how you can use K to find delta G, or delta G to find K. And if you needed to, you could use K to find delta G.